Welcome to day 16 of the Advent of Code. Today is all about decoding train tickets. A ticket is basically a sequence of numbers, and every one of those numbers is or belongs to a field. So it could be class, row, or seat. And in order to constrain the possibilities, we have rules for those fields that state the class must be between 1 and 3 or 5 and 7. The row must be between 6 and 11 or 33 to 44 and so on. So for example, the number 1 can't possibly be the row because 1 lies in neither range. Okay, it also can't be the seat, so obviously it must be the class, right? Okay, and in case we can't figure this out from just looking at our own ticket, we can look at nearby tickets as well. Okay, then I already prepared all the long and tedious parsing. So for example, the parse rules function takes the field rules as an input, as a string, and then returns a sequence of vectors where the first element is the field, and then the next four numbers define the first range and the second range. Okay, and we use good old, regular regular expressions, destructuring, and then conversion from string to int. For the rules for the ticket, it's even simpler. We just want to convert these comma-separated values into a map of numbers. That's almost trivial. And then the complete parsing function just combines the functions above. Here you see parse rules, and here you see the parse ticket. So we get a map back with a rules, ticket, and nearbys entry. We already saw those outputs above, and here we have just a sequence of tickets. Okay, not interesting, but very tedious to write. But I think we saw parsing enough times now. Okay, so then for part 1, I prepared some helper functions that will provide useful services for us. So here, for example, the satisfies rule helper function. It takes a number and a rule, and we should check if the number is valid according to the rule. For example, here it's invalid because 4 is too big for the first range and too small for the second range. Okay, and here we already destructure. The name is not interesting, and these 4 numbers are interesting. So it's quite simple. We can simply OR two conditions, smaller than or equal to min1 number max1, and the alternative is smaller than or equal to min2 number max2. Right? So it's quite nice that we can use smaller than or equal to with more than 2 arguments. Okay, let's not forget to compile. I always forget that. Then we have an invalid number helper function. It's given a number and a sequence of rules. And if the number is invalid, for our case, 4 lies between those ranges, is too small for the first range and too small for the second range, then I want to return the number itself. Otherwise, I want to return nil. That's maybe a bit unusual that we don't simply return a Boolean here, but we need those invalid numbers for part 1. Okay, so how could we solve this? So there's a useful function called sum. It takes a predicate and a collection. In our case, the collection are the rules, and the predicate should simply check if satisfies rule, number, and rule, and in our case, the rule comes from the rules that we sum over. Okay, so then we would get, what would the sum return? It would give us a rule, the first rule that matches, and otherwise we get nil. But if it gives us a rule, then we have a valid number. So if we get a rule, we want to return nil because the valid ones are not interesting for us, and otherwise we want to return the number. Okay, and this pattern of saying if the condition is true, I want to return nil and otherwise number, there's a special function for that called if not, where the nil case is implied when you don't have an else. Okay, so we save one line of code. Okay, cool. And then this function, how does it differ from the first one? It differs in the first parameter. It doesn't take a single number, but a vector of numbers. And we should find the first number that is invalid, basically. Okay. So we can use the sum function again. Which parameters do we want to use. So here we want to sum over the ticket because we want to find the first one that contains or that is an invalid number basically. Okay, and here we can simply delegate to the function that we just wrote. It takes a number and it takes rules, and the number comes from our ticket. That's why it's the placeholder here. Okay, so that's also looking good. Okay, cool. So now we can start doing useful stuff. What are we supposed to do? We're supposed to find all the invalid numbers and then add them up. How could we do that? Let's start with the nearbys and maybe look at them. Okay, so these are the nearby tickets. And I think in the first one there is no invalid number, and in the last three there is one invalid number each. So let's simply map the sum invalid number function over it. It takes number, it takes rules, and right, we get in the tickets, so this should be the number. No, I'm sorry, this is not the number. This is the vector here, right? The complete ticket. This is one ticket, and we map over the tickets. Okay. That's interesting. Parent at the wrong place. Yeah, we can see that due to the indentation. Very nice. Okay, so now we see the first ticket has no invalid number, and the three tickets have one. And we're not really interested in the nil. How do we get rid of the nil? We can simply remove all the elements that are nil. Remove is just the opposite of filter. You already know that. And nil simply checks for nil. Okay, so now the nil is gone, and we can reduce via plus, and then we get a sum for the small and for the large input. Yeah, about 22,000. I remember that being the correct number. Okay, so for part one, the most interesting stuff was the sum function, and I think the if not macro. I don't think we have seen that before. Okay, and otherwise some logic, of course. Okay, so for part two, we are supposed to find out which values belong to which field, and a good helper function for that is this applicable rules helper function. So we give it a column, that would be the first numbers of all the nearby tickets, for example, and a complete list of all the rules that we care about. And then in this case, it should only output a single rule in a sequence. Why is it this one? Let's see. So if we look at the first value 3, that's invalid for the first rule, so we already throw that away. It's valid for the second rule and also valid for the third rule. Okay, and then for 15, we don't even look at the first one anymore, it's already eliminated. 15 fits the second rule, but not the third rule. And then 5 fits the leftover second rule. So that's why only the second rule is returned. Okay, cool. So how would we implement this? We can use our good friend reduce once more, f, val, and col. What do we want to reduce over? We want to reduce over the column, right? We want to, just as I showed you in the example, we iterated over the column basically. And our starting value should be all the rules, because from the start we can't rule any of those rules out. And then our function, our reducing function, takes the rules and the number, and then we must constrain the rules. We can do that with a filter. We can say satisfies rule number placeholder rules. Okay. So we look at the rules so far and say we don't want to keep all of them, only those that satisfy the rule with a given number that we are passed from the columns. Okay, let's see, that compiles. Then the next helper function, I made it a little more general than it has to be for this example, but I think this is easier to understand. So let's say we have a map where A and C are already contained. And then here we have a vector with A, B, and C. So B is the only unique key in this vector, basically, if you look at the map. B is new. And then we have a value that we want to associate in the map. And so we choose B to associate to 123. Okay, because A and C are already used in the map. Okay, so how could we implement that? We could say the uniques inside the vector is remove M keys. What does this mean? It means we want to look at all the keys that we still have or that were passed in, and we want to use the map as the predicate. And you know, maps are functions, so we can use them as predicates. If the key is already in a map, it will return, you know, 42 or 97. That's basically true, so it will be removed. And if it isn't in the map, like B, we will get nil, so it will the key will survive. Okay, so this doesn't mean that we want to remove something from a map. It means we want to remove from the keys based on this predicate, which is a map, which is a function, which is a valid predicate. Okay, and in our case, we know that there's only ever one unique value in the vector. So we can immediately destructure and get rid of the plural. Okay, and what do we want to do next? Now we want to associate the map unique key value. Okay, so that should work. Okay, so now we can do the interesting stuff. Let's start with the nearbys again. Here, that's quite a lot of numbers for the large input. Okay, and now first we have to remove all the invalid tickets. We already know remove. So a predicate and a collection. Right, so the collection is of course passed in by the macro, by the threading macro. So we can remove some invalid number rules, right? So this would be one of the tickets. Okay, and then not all of them survive. Okay, and now we want to do something that is probably mathematically very interesting. So let's say we have, this is basically a shorthand version of all these numbers. And then we have the next numbers and so on. And now we are interested in combining all the first numbers, because that's a column that we want to check. Then all those numbers, because that's the next column that we want to check. And then all those numbers. If you know in mathematics how this is called, let me know. So what we can do is say, I want to apply the map vector over all those. And as you can see, before we had a vector of rows, and now we have a vector of columns. So is this like rotation of a matrix or something? Or I'm not really sure how this is called. Okay, and that's exactly what we want to do here. So we want to apply map vector. And we need the apply because without the apply, we just get an additional sequence around the input. That's not what we want, right? We need to take these and pass it to the vector function. We don't want to pass the entire vector to the vector function. That wouldn't be useful. Okay. Cool. So now we have our columns here. And now we can map a function over it. Let's use the map indexed. We get an index and a number. And then we say we want to return a vector with the applicable rules for number and rules, and then the index. Yeah, I think that's already looking quite interesting. So what exactly did we do here? So these columns that we just saw, we pass to applicable rules, and you know that applicable rules returns a sequence of all the rules that apply to that column. Okay, and that's quite a lot, unfortunately. So for example, where does this even end? So for example, for column 0, all these rules would be legal. For column 1, all those would be legal. Well, that's quite a lot. Oh, this is interesting. So for column 3, only a single one is legal. So we know that column 3 must be the type. So it can't be column 2. We rule that out basically. Okay. Yeah. And here's one with 3. Do we also have one with 2? It's probably not so easy to find. Yeah, we will find it. Okay, so it's probably easier to find the you know, the one with only one possible rule and the one with only two possible rules, if we simply sort the result with a sort by function. So we get the rules and the index. Okay, and then we can simply count the rules. And that's already more revealing. So here's again our column number 3, which can only be type. Column 17 could be the type or the row, but since we already, you know, assigned the type to column 3, then we know that type must be column 17. And here we can see for column 6, it could be arrival platform, row, or type, but we already assigned row and type to the previous 2 columns here. So column 6 must be the arrival platform, and so on. So the next one is 4 possible rules where 3 are already assigned. The next one is 5 where 4 are already assigned, and so on. Okay, so this should be doable, and that's exactly where the associate_unique function comes in. So if we reduce our associate_unique function and start with an empty map, because initially we don't have any associations between rules and indices, then we get this interesting result. Okay, so arrival location must be 15, seed must be 16. Do we find our column 3 and 6 back? Yeah, here you can see the column 6 that we deduced should be the arrival platform, and then we had 3 and 17, right? Here's 3, which was the type, and 17 is here, which was the row. Right? So these were all correctly deduced. That's quite nice. Okay, cool. So that was that. And then we're only interested in the rules or the fields that start with the string departure. So that would be, for example, this one here. So let's filter and say, what do we get in? We get here a rule and an index, right? A rule and an index. But we're only interested in the name of the rule, so we can immediately destructure one level more like this. And then we can say string starts with, and then does the name start with departure space. Then we should only have 6 left. Yeah, that's looking good. Right, and then we should basically look up those indices on our own ticket. How would we do that? Right, we can say a function that takes a rule and an index. Okay, the rule is not interesting to me, so I could write underscore, but I find it easier to understand with the name, even if we don't use it. And then we can simply say ticket at index. You remember that vectors are functions of their indices, right? Okay, and then we should get 2, 19, 12, 9, 7, and 18. Oh, right, no. That would be the index itself. Let me do it like this. Yeah, here are the indices themselves. And if we look them up in our vector, of course, we get the concrete values noted on our own ticket. Okay, and then all that's left to do is reduce them via the times function, because this time we're not supposed to add them, but multiply them. And then we get a very, very large number. Okay, cool. So for part 2, again, not so much interesting Clojure stuff. Yeah, good old reduce, filter, maps. Yeah, not really that interesting from a Clojure perspective. So what I found hardest was the apply map vector to rotate a matrix or whatever it's called. Please let me know. And then the insight that it makes sense to sort by the number of possible rules. But once you have that insight, it's a trivial in hindsight, of course, as often. And then the associate_unique function came in handy then, and the rest was just, business as usual. So, as always, I'm very interested in your feedback. Did I overcomplicate something? Can this be written in, half the lines? Can I fuse some lines? I don't think it's the most beautiful code because it's a lot of stuff to digest. Let me know if you found a better solution.